Moving on to the next digital circuit, encoder. What is an encoder? Encoder is a digital circuit which has got 2 to the power n input lines and only n output lines. Example, if there are 4 input lines, then it can be written as 2 power 2. That power 2 will be reflecting at the output. So, a 4:2 encoder. If there are 8 input lines, that encoder will have 8 can be written as 2 power 3, that 3 is here, and that digital circuit should have 3 output lines. Similarly, if I take an example of 64, 64 can be written as 2 to the power 6. So, that power 6 should be the number of output lines of an encoder. An encoder does exactly the opposite of a decoder, what we have discussed in the previous session. Whichever line is active at the input, that line's binary index, if the fifth line, fifth channel, input channel is active, then the binary code corresponding to number 5 will be represented on the output lines. So, we can say an encoder is a digital circuit with many input lines and few output lines. It is also called as many to few. Here we have 4 input lines, D0, D1, D2, D3. So, 4 can be represented as 2 power 2. So, that power 2 will be here at the output. So, understanding how to generate or how to write a function describing a 4 input line to 2 output line encoder. Suppose D0 is the channel which is active, D0 is logic high. So, at the output we should obtain the index 0 0 corresponding to D0. If we have D1 going high, this D1 is high, then here at the output we should be getting a binary index representing 1. So, that is 0 1, we will have 0 here, 1 here. If you have D2 going high, then the index at the output should represent 2, that is 1 0. That is how we are going to write the function table. Now, if we select a 8:3 line encoder, then if D0 is high at the output of the encoder, we should have an index 0 0 0 representing the value D0. If D3 goes high, then the corresponding code should be 0 1 1 at the encoder's output. So, whichever channel goes high at the input, the index of that channel should be provided at the output lines. That is the function of a encoder circuit. So, we have a 4:2 line encoder, and we have a 8:3 line encoder. A question arises, what will be the output index if you activate 2 or 3 lines together at the input? In such case, there will be a contradiction or a conflict. For that reason, we go with this idea known as the design of priority encoder. In this design, we will try to represent a functional table in order to avoid this conflict at the output. We will resolve the conflict by assigning a priority. We will say the highest channel out of 2 to the power n should have the priority. That gives us a priority encoder with the highest priority assigned to the MSB. Contrary to that, we can also have a encoder which has got a priority to the LSB. So let us understand this functional table of a priority encoder. What is this saying? There are don't cares from D7 to D1 and there is 1 year, which means irrespective of all these higher channels D7, D6, D5, D4, D3, D2, D1, if the lowest channel D0 is high, then the output will simply be the binary index of D0, that is 0, 0, 0. The encoder will only output the binary index of the lowest channel. Now, let us try to understand the second row. What is this saying? There are don't cares, which means it can be either 0 or 1. And look here, the D0 channel should be 0. D0 should not be activated. If you press D0 and all other 6 or 7 channels, again the encoder will simply output as 0. So, we are trying to write a functional table for a priority encoder with the highest priority given to the LSB. So, if D0 is off and you have pressed all other channels starting from D7 to D1, then the output code of the encoder, output will represent the roll number, the binary index of channel number 1 in the form of 0, 0, 1. Let us see what is this saying. Let us go to the last table. Like this, you can analyze all the rows. Provided the LSBs are off, then the lowest of these channels will be selected, or those index will be at the output of the priority encoder. Let us try to understand the last row, because here we can find no don't cares. What is this indicating? If the encoder should output or should select D7, all the lower values channel, all the channels with a lower index than 7 should be off. That is why we have zeros all over this place. Once D7 is high and all other channels are low, they are not been pressed, then the priority encoder will output this index 111, which is nothing but the binary code for channel number 7. This is how the functional table for a priority encoder with the priority assigned to LSB. If you press all 7 together, only D0's roll number binary index will be put at the encoder's output. If you press D1 to D7 and you have left D0 untouched, in such case only D1's code will be available at the output. So, we can have one more design of a priority encoder. Instead of assigning the priority to the LSB, we will try to make D7 or the MSB as the higher priority channel. Let us design an encoder, a priority encoder which has a priority assigned to the higher order channel or the MSB. So, this is the function table of a priority encoder with the priority given to the MSB. How to understand this function table? If I want to check or if I want to see an index of 0, 0, 0 at the output of the priority encoder, then only D naught should be high. All higher order channels compared to D naught. Higher channels compared to D naught means D1, D2, D3, D4, D5, D6 and D7. These channels should be off. Only in such case we can expect a binary index of 0, 0, 0 representing D naught at the output of the encoder. What is this indicating? Second row. We see a don't care in a D naught column, 1 in a D1, all channels starting from D2 up to D7, they are zeros. This means if you press D1 and you don't press D naught, which means D naught is off, D1 is high, all other channels starting from D2 to D7, they are off. In such case, we have 0, 0, 1 as the index at the output of the encoder representing D1 is high. Now, we know the value of don't care can be either 0 or 1. In the earlier case, I had selected a value of 0 for this don't care. Now, if I assume this as 1, if this don't care is now 1, what is the situation? In this encoder, we have pressed D1 along with D naught. We have pressed D1 and D naught. Two channels are high simultaneously. This is a design for the priority being given to or assigned to higher channel. Out of D1 and D naught, which is high, D1 is high. Therefore, irrespective of the status of the lower channel D naught, the output of the encoder will be 0, 0, 1, which means D1 is high. Now, what is this indicating? Irrespective, suppose if you see that all D3, D4, D5, D6 and D7 are off and you have pressed D0, D1, D2. Out of these three channels, which is the highest one? D2. D2's code or index will be at 0, 1, 0 at the output. If you press D1, D0 along with the D2, obviously the higher channel is D2, that channel's code should be at the encoder's output. Now, let us look into this. What is this row indicating? D7, suppose D7 is off and we have pressed D6, irrespective of D0, D1, D2, D3 up to this point, the channel index will be 110 at the encoder, means the highest channel of all these is a D6, that is high, means that particular channel's index will be available at the output of the encoder. What is the last row here indicating? D7 goes high. Irrespective of all lower order channels, the index of D7, which is binary 1, 1, 1, will be shown at the output of the encoder. Whether you press all 7 channels, what is the output? It is 7. If you press only 7th channel and you don't press any other lower channel, still the output will be 7. If you press the 7th channel, the 6th channel, the 5th channel and assume the 2nd channel, we are pressing these many channels at the input, yet out of all the active channels, out of all the channels pressed at the input, which is the channel which has got the highest index, that is 7. then obviously that particular channel's index has to be at the output of the encoder. So, this is how the priority encoder with the priority assigned to the highest channel works. So, now going back to the beginning, we had discussed about different styles of describing a logic circuit. You can describe that in terms of its behavioral description, you can go with the data flow description, you can go with the structural description. Now, look at this. This functional table appears very cumbersome for me to obtain a logical equation. So, it is not impossible, but it is quite difficult. In such situation, I can simply transform this table into a HDL statement, which is known as the behavioral description, and still it is possible for me to obtain this kind of equation and this logic connection and synthesize the netlist, supply that to a robot and get a 8:3 priority encoder synthesized. So, that is how all the data flow description, the behavioral description as well as the structural description can be made used in synthesizing the netlist of a digital circuit using a HDL CAD tool. Now, let us look into the applications of encoders. Encoders, similar to decoders, they are present in the processors, especially where a serial communication protocol is being implemented. Various serial communication protocols within the processors as well as in the communication network and other data transfer applications all have a digital circuit known as the encoder built within them. The next task is to write the HDL code in Verilog to implement the encoder.